Howdy. I'm just some random nude dude sitting in my closet talking to myself. It's where I celebrate the power of free thinking and encourage bold ideas. As a society, we're often afraid to challenge the norms and think outside the box. But here, I embrace the unconventional. So sit back, relax, and join me on this journey of exploration where we embrace our inner nude dude and push the boundaries to discover new perspectives. Quantum computing is a revolutionary technology that has the potential to transform the way we process information and solve complex problems. It's a field that combines elements of physics, mathematics, and computer science, and is based on the principles of quantum mechanics. Quantum computers are incredibly powerful machines that can perform certain calculations much faster than classical computers, allowing us to solve problems that are currently considered intractable. You may be wondering what makes quantum computing so special and why it's important. Simply put, quantum computing has the potential to revolutionize many fields, including cryptography, drug discovery, optimization, machine learning, and material science. It's a technology that could help us solve some of the world's most pressing problems, from climate change to disease treatment. In this video, we'll be exploring the basics of quantum computing, including its history, how it works, and its potential applications. We'll also dive into the relationship between quantum computing and artificial intelligence, or machine learning, and provide some examples of how quantum computing is being used to improve these fields. By the end of this video, you'll have a better understanding of what quantum computing is, how it works, and why it's such an exciting and important field. So let's get started and explore the fascinating world of quantum computing. Quantum computing is a type of computing that relies on the principles of quantum mechanics to perform complex calculations. Unlike classical computing, it uses bits that can only have two values, 0 or 1. Quantum computing uses qubits, which can exist in a superposition of multiple states. This means that a qubit can be worth both 1 and 0 at the same time, allowing quantum computers to perform certain calculations exponentially faster than classical computers. One of the most well-known examples of a problem that can be solved faster with quantum computing is factoring large numbers. Factoring large numbers is an important problem in cryptography, as it forms the basis of many encryption algorithms. Classical computers struggle to factor large numbers efficiently, which is why many encryption methods are considered secure. However, a quantum computer can use a mathematical algorithm called Shor's algorithm to factor large numbers quickly and efficiently. Another example of a problem that can be solved faster with quantum computing is simulating the behavior of molecules. Understanding how molecules behave is important in fields such as drug discovery and material science. But simulating the behavior of even moderately sized molecules can take classical computers a long time. With a quantum computer, however, simulating the behavior of molecules becomes much easier, allowing researchers to design new drugs and materials that are more efficient than those currently available. Quantum computing can also be used to optimize complex systems such as traffic flows or energy grids. These systems involve many variables that need to be optimized to achieve the best possible outcome. With a quantum computer, it becomes possible to explore many more possible solutions than is feasible with a classical computer, leading to more efficient and sustainable systems. Quantum computing is a powerful tool that can solve certain problems much faster than classical computers. Its ability to perform complex calculations in parallel and explore many possible solutions simultaneously makes it promising technology for a wide range of applications, from cryptography to drug discovery to optimizing complex systems. One of the earliest references to quantum computing can be found in the science fiction novel Hitchhiker's Guide to the Galaxy by Douglas Adams. In the book, a group of hyper-intelligent beings build a supercomputer named Deep Thought to calculate the answer to the ultimate question of life, the universe, and everything. Deep Thought uses quantum computing to perform the calculation, which turns out to be, spoiler alert, 42. This reference has become a cultural icon and is often referenced in popular culture and technology. Another example of a historical reference to quantum computing can be found in the work of physicist Richard Feynman. In 1982, Feynman proposed the idea of using quantum computers to simulate quantum mechanical systems, which are difficult to simulate using classical computers. Feynman's proposal laid the theoretical groundwork for the development of quantum computing and is still influential in the field today. In the 1990s, Peter Shor, a mathematician at AT&T Bell Labs, developed an algorithm for quantum computing that could solve the problem of factoring large numbers. Shor's algorithm is considered one of the most important algorithms in the field of quantum computing, and is a major reason why quantum computing is considered a potential threat to classical cryptography. More recently, in 2019, Google announced it had achieved quantum supremacy with its quantum computer, Sycamore. Google claimed that Sycamore had performed a calculation in 200 seconds that would have taken the world's most powerful supercomputer 10,000 years to complete. The announcement generated a lot of excitement and speculation about the potential of quantum computing. There have been many historical references to quantum computing in science fiction, theoretical physics, and computer science. These references have helped to inspire and shape the development of quantum computing, which is now considered a promising technology with many potential applications. Cryptography is the practice of secure communication, which involves the use of codes and ciphers to protect information from unauthorized access. Currently, most cryptographic algorithms are based on the difficulty of factoring large numbers, a problem that is considered intractable with classical computers. However, quantum computers have the potential to break many of these algorithms, which could have serious implications for cybersecurity. Quantum computers are able to use a mathematical algorithm called Shor's algorithm to factor large numbers significantly faster than classical computers. This means that many of the cryptographic tools that we use today could be broken with a large enough quantum computer. This includes protocols such as RSA and elliptical curve cryptography, which are widely used to secure internet communication, online transactions, and other sensitive data. To address this potential security threat, researchers are working on developing new cryptographic protocols that are resistant to attacks by quantum computers. One promising approach is the development of quantum-resistant cryptography, which involves using cryptographic protocols that are designed to be secure against attacks by both classical and quantum computers. Another approach is the development of quantum key distribution, which uses the principles of quantum mechanics to distribute encryption keys that are resistant to eavesdropping. This approach relies on the fact that any attempt to intercept a quantum key would alter its quantum state, which would be detectable by the sender and receiver. While quantum computing has the potential to break many of the cryptographic protocols that we use today, researchers are working on developing new approaches to ensure the security of our information in a post-quantum world. As this technology continues to develop, we can expect to see more and more applications of quantum computing in the field of cryptography, ultimately leading to more secure and private communication for individuals and organizations around the world. Drug discovery is a process that involves identifying and developing new medications to treat diseases. This process can be time-consuming and expensive, and requires significant resources and expertise. However, quantum computing has the potential to revolutionize this field by allowing us to simulate and analyze complex molecular interactions much more efficiently than classical computers. One of the key challenges in drug discovery is understanding the structure and behavior of molecules. Classical computers struggle to accurately simulate the behavior of molecules due to the sheer number of variables involved. Quantum computers, on the other hand, can perform calculations using qubits, which can exist in a state of superposition, allowing them to explore many possible molecular configurations simultaneously. This ability to explore many possible configurations simultaneously can greatly speed up the drug discovery process. By running simulations on quantum computers, researchers can identify potential drug candidates much more quickly and accurately than with classical computers. This could help accelerate the development of new drugs and potentially lead to more effective treatments for a wide range of diseases. In addition, quantum computing can also be used to optimize drug dosages and reduce the risks of side effects. By simulating how different drugs interact with the body, quantum computers can help researchers identify the optimal dosage for a given patient, while minimizing the risk of negative side effects. Quantum computing has the potential to greatly accelerate the drug discovery process, leading to more efficient treatments for a wide range of diseases. As this technology continues to develop, we can expect to see more and more applications of quantum computing in the field of drug discovery, ultimately leading to better health outcomes for patients around the world. Traffic flow is a complex and dynamic system that allows the movement of vehicles, pedestrians, and other modes of transportation on roads and highways. Traffic congestion is a major problem in many cities around the world, leading to wasted time, increased pollution, and reduced quality of life for residents. However, quantum computing has the potential to help address this problem by optimizing traffic flow and reducing congestion. One of the key challenges in optimizing traffic flow is the sheer number of variables involved, including the number and speed of vehicles, the layout of the road network, and the behavior of drivers. Classical computers struggle to accurately simulate traffic flow due to the complexity of these variables. However, quantum computers are able to perform calculations using qubits, which can exist in a state of superposition, allowing them to explore many possible traffic scenarios simultaneously. This ability to explore many possible scenarios simultaneously can greatly improve our understanding of traffic flow and help us identify optimal solutions for reducing congestion. For example, quantum computing could be used to optimize traffic signal timings, route vehicles more efficiently, and predict traffic patterns in real time. This could lead to significant improvements in travel time, fuel consumption, and air quality, ultimately improving quality of life for residents and reducing the negative impact of traffic on the environment. In addition to optimizing traffic flow, quantum computing can also be used to develop more efficient and sustainable transportation systems. For example, quantum computing could be used to optimize the design of electric vehicles and their charging infrastructure, leading to more efficient use of resources and reduced emissions. Quantum computing has the potential to greatly improve traffic flow and reduce congestion, ultimately leading to more efficient and sustainable transportation systems. As this technology continues to develop, we can expect to see more and more applications of quantum computing in the field of transportation, ultimately leading to a more connected, efficient, and sustainable world. Machine learning and AI are fields that involve using algorithms and statistical models to analyze data and make predictions or decisions. Quantum computing has the potential to significantly accelerate the training of these models and enable new types of machine learning and AI applications. One of the key advantages to quantum computing in the field of machine learning is the ability to perform calculations on large data sets simultaneously, using qubits that can exist in multiple states at once. This enables researchers to analyze complex patterns and relationships in data that would be difficult or impossible to detect using classical computing. Quantum computing can also be used to develop new machine learning algorithms that are specifically designed for quantum computers. These algorithms could be used to solve problems that are considered intractable with classical computers, such as simulating the behavior of complex molecules or optimizing financial portfolios. In addition to accelerating machine learning, quantum computing could also be used to improve the accuracy of AI systems. For example, a quantum computer could be used to develop more sophisticated models for natural language processing and computer vision. This could lead to more accurate and nuanced AI systems. Finally, quantum computing could be used to improve the privacy and security of AI systems. Quantum key distribution, for example, could be used to distribute encryption keys that are resistant to eavesdropping, making it more difficult for hackers to compromise AI systems. Quantum computing has the potential to significantly improve the field of machine learning and AI, enabling new types of applications and accelerating the training of complex models. As this technology continues to develop, we can expect to see more and more applications of quantum computing in the field of machine learning and AI, ultimately leading to more advanced and accurate AI systems for a wide range of industries and applications. Quantum annealing is a computational technique that involves using a quantum processor to find the global minimum of a complex optimization problem. In other words, it's a way to solve problems that are difficult or impossible to solve using classical computers. The technique works by encoding the problem as a so-called Ising model, which describes a set of interacting spins. The quantum processor then seeks to find a configuration of spins that minimizes the energy of the system, using quantum tunneling and quantum entanglement to explore multiple possibilities simultaneously. While quantum annealing is not a general-purpose computational method, it has shown promise in solving certain optimization problems, particularly those that involve finding the ground state of a complex system. One potential application of quantum annealing is in optimizing the placement of energy storage systems on the grid with the aim of reducing congestion and improving energy efficiency. The management of energy grids is a complex and multifaceted task that requires balancing the supply and demand of energy across a large and often interconnected network of power plants, transmission lines, and distribution systems. One of the key challenges of energy grid management is the optimization of power flow. This involves determining the most efficient way to transmit power across the grid, taking into account factors such as distance, capacity, and potential congestion. Quantum computing has the potential to help address this challenge by exploring multiple possibilities in parallel and processing large amounts of data more quickly and efficiently than classical computers. For example, researchers have proposed using quantum annealing to optimize the placement of energy storage systems on the grid, with the aim of reducing congestion and improving energy efficiency. Another potential application of quantum computing in the energy grid management is the prediction of power demand. Accurately forecasting the amount of power that will be needed at different times and locations on the grid is essential for ensuring the stable and reliable energy supply. Quantum computing can potentially improve the accuracy of these predictions by processing complex relationships between different variables, such as weather patterns, consumer behavior, and energy consumption trends. Finally, quantum computing could also be used in the development of new energy storage technologies, such as batteries and capacitors, that store energy more efficiently and effectively. For example, researchers are exploring the use of quantum materials in energy storage devices, which could potentially increase the energy density and storage capacity of these devices. Overall, the potential applications of quantum computing in energy grid management are numerous and wide-ranging, and hold the promise of transforming the way we generate, distribute, and consume energy. Materials management is a critical aspect of many industries, including manufacturing, supply chain management, and logistics. The efficient management of materials can lead to significant cost savings and improved productivity. Quantum computing has the potential to revolutionize the way we manage materials by optimizing logistics, reducing waste, and improving supply chain transparency. One of the key challenges in materials management is the complexity of the supply chain. Materials may be sourced from multiple suppliers, transported across different modes of transportation, and stored in multiple warehouses before being used in the manufacturing process. Optimizing the process requires the analysis of large amounts of data, including delivery times, inventory levels, and transportation costs. Classical computing struggles with these type of calculations due to the sheer number of variables involved. However, quantum computing has the potential to analyze these variables and identify the optimal solution much faster and more accurately than classical computing. For example, quantum computing could be used to optimize the delivery routes and scheduling of shipments to reduce transportation costs and minimize the environmental impact of logistics. Quantum computing could also be used to optimize inventory levels, leading to reduced waste and improved supply chain efficiency. In addition, quantum computing could be used to improve the transparency and security of the supply chain. Blockchain technology, for example, could be used to create a secure and transparent ledger of all transactions in the supply chain, ensuring that all parties have access to accurate information about the location and status of materials at all times. Quantum computing has the potential to revolutionize materials management by optimizing logistics, reducing waste, and improving supply chain transparency. As this technology continues to develop, we can expect to see more and more applications of quantum computing in the field of materials management, ultimately leading to a more efficient and sustainable supply chain for a wide range of industries. As you can see, quantum computing has many potential applications in a wide range of fields, including cryptography, drug discovery, optimization, machine learning, and materials science. As quantum computing technology continues to develop, we can expect to see more and more applications of this powerful technology in our daily lives. Quantum computing also has the potential to revolutionize artificial intelligence and machine learning. One of the key challenges in these fields is processing large amounts of data quickly. Quantum computers can help by performing complex calculations faster than classical computers. This can lead to more accurate predictions and better machine learning models. One of the main applications of artificial intelligence and machine learning is in the field of optimization. Many real-world problems, such as resource allocation, scheduling, and logistics, involve optimizing a large number of variables to achieve the best possible outcome. This optimization problem is computationally challenging and requires a lot of computing resources. Quantum computing has the potential to speed up the optimization process by exploring many more possible solutions simultaneously than is feasible with classical computers. Optimization is a critical aspect of many industries, including finance, logistics, and engineering. The goal of optimization is to identify the best possible solution to a problem, given a set of constraints. Quantum computing has the potential to revolutionize optimization by solving problems that are considered intractable with classical computing. One of the key advantages to quantum computing in the field of optimization is the ability to analyze multiple potential solutions simultaneously, using qubits that can exist in multiple states at once. This enables researchers to analyze complex optimization problems that would be difficult or impossible to solve using classical computing. For example, quantum computing can be used to optimize financial portfolios by analyzing large amounts of data and identifying the optimal allocation of assets. This could lead to higher returns and reduced risk for investors. In addition, quantum computing could be used to optimize logistics and supply chain management. For example, quantum computing could be used to identify the most efficient routes for delivery trucks, minimizing transportation costs and reducing carbon emissions. Finally, quantum computing could be used to optimize engineering designs and simulations. For example, quantum computing could be used to simulate the behavior of complex systems, such as the flow of fluids through pipes or behavior of materials at the atomic level. This could lead to more accurate predictions and better designed products. Quantum computing has the potential to revolutionize optimization by solving problems that are considered intractable with classical computing. As this technology continues to develop, we can expect to see more and more applications of quantum computing in the field of optimization, ultimately leading to more efficient and effective solutions for a wide range of industries and applications. Deep neural networks, DNNs, are a type of artificial intelligence that are used to solve complex problems in a wide range of industries, including image recognition, natural language processing, and self-driving cars. DNNs are particularly effective at processing large amounts of data and identifying patterns and relationships in that data. However, training a DNN can be a computationally intensive process that requires large amount of processing power and memory. Classical computers can struggle to keep up with the demands of training a DNN, particularly as the size and complexity of networks increases. This is where quantum computing comes in. Quantum computing has the potential to speed up the training of DNNs, allowing them to process more data and identify more complex patterns and relationships. In particular, quantum computing can be used to accelerate the process of computing the inner products between large vectors, which are a key component of DNN training. One of the most promising applications of quantum computing in the field of DNNs is in the development of quantum neural networks, QNNs. QNNs are a type of neural network that are designed to run on quantum computers, taking advantage of the unique capabilities of quantum computing to speed up training and improve accuracy. While QNNs are still in the early stages of development, they have already shown promise in a number of applications, including image recognition and natural language processing. For example, a QNN developed by researchers at IBM was able to classify images with 97% accuracy, outperforming classical neural networks. Quantum computing has the potential to revolutionize the field of deep neural networks by speeding up training and improving accuracy. As this technology continues to develop, we can expect to see more and more applications of quantum computing in the field of artificial intelligence, ultimately leading to more powerful and effective AI systems. Clustering and classification are two common tasks in machine learning that involve grouping data points based on similarities and identifying patterns and relationships in the data. These tasks have applications in a wide range of industries, from finance to healthcare to marketing. Classical machine learning algorithms for clustering and classification can be limited by the size and complexity of the dataset, as well as the computational resources required to process the data. Quantum computing has the potential to overcome these limitations by processing data in parallel and exploring all possible solutions at once. One of the key advantages to quantum computing in the field of clustering and classification is the ability to perform complex mathematical operations on high-dimensional datasets. This is particularly useful for applications like image recognition, where the data consists of a large array of pixels. In addition, quantum computing can be used to develop new algorithms for clustering and classification that are better suited for capabilities of quantum computers. For example, researchers have developed a quantum algorithm for clustering that outperforms classical algorithms on certain types of data. Another promising application of quantum computing in clustering and classification is in the field of unsupervised learning. Unsupervised learning involves identifying patterns in data without the use of predefined categories or labels. Quantum computing has the potential to accelerate unsupervised learning by exploring all possible solutions in parallel, allowing researchers to identify patterns and relationships in the data more quickly and accurately. Quantum computing has the potential to revolutionize the field of clustering and classification by overcoming the limitations of classical computing and developing new algorithms better suited for quantum computers. As this technology continues to develop, we can expect to see more and more applications of quantum computing in the field of machine learning, ultimately leading to more powerful and effective machine learning systems. Reinforcement learning is a type of machine learning that involves training an agent to make decisions in an environment based on rewards or punishments. This type of learning is used in a variety of applications, such as game playing, robotics, and finance. Reinforcement learning algorithms can be computationally intensive, as they require processing large amounts of data and exploring different possibilities to determine the optimal actions for the agent to take. Quantum computing has the potential to speed up the process by exploring all possible solutions in parallel, allowing the agent to learn and make decisions more quickly. One of the key advantages of using quantum computing in reinforcement learning is the ability to explore a large number of potential solutions at once. This is particularly useful in environments with large numbers of variables or states, where classical computing may struggle to explore all possible options. In addition, quantum computing can be used to develop new reinforcement learning algorithms that are better suited for the capabilities of quantum computers. For example, researchers have developed the quantum algorithm for solving the multi-armed bandit problem, which is a classic problem in reinforcement learning that involves balancing exploration and exploitation to maximize rewards. Another promising application of quantum computing in reinforcement learning is the development of quantum reinforcement learning algorithms that can learn from quantum data. These algorithms could be used in applications such as quantum control and quantum chemistry, where quantum data is used to make decisions. Quantum computing has the potential to revolutionize the field of reinforcement learning by accelerating the learning process and enabling the development of new algorithms better suited for quantum computers. As this technology continues to develop, we can expect to see more and more applications of quantum computing in the field of machine learning, ultimately leading to more powerful and effective machine learning systems. As you can see, quantum computing has the potential to significantly improve the performance of artificial intelligence and machine learning algorithms in a wide range of applications, including optimization, deep learning, clustering, classification, and reinforcement learning. As quantum computing technology continues to develop, we can expect to see more and more applications of this powerful technology in the field of artificial intelligence and machine learning. Quantum computing is a groundbreaking technology that has the potential to revolutionize many fields, from cryptography and drug discovery to optimization and machine learning. It's a field that has seen tremendous progress in recent years, and many experts believe that quantum computers will soon be able to solve problems that are currently considered intractable with classical computers. As we continue to develop this technology, we must also be mindful of the potential risks and challenges associated with it. Quantum computing has the potential to disrupt current encryption methods, which could have serious implications for cybersecurity. Additionally, the development of quantum computers requires significant resources and expertise, which could create a digital divide between countries and companies that have access to this technology and those that do not. Despite these challenges, the potential benefits of quantum computing are too great to ignore. It's a technology that could help us solve some of the world's most pressing problems, from climate change to disease treatment. As we move forward, it's important to continue investing in quantum computing research and development, while also being mindful of the potential risks and challenges associated with this powerful technology. So whether you're a scientist, a student, or just some random nude dude, I hope this video has given you a better understanding of what quantum computing is, how it works, and why it's such an exciting and important field. Thanks for tuning in. I hope you found this video informative and thought-provoking. This is the point at which others tell you, if you enjoyed it, please give it a thumbs up and consider subscribing to our channel for more content like this. But we all know that kind of thing is for losers. Don't be a loser. And as always, I welcome your feedback and ideas for future videos in the comments section below. Until next time, keep exploring, keep learning, and keep embracing your inner nude, dude.